Okay, this is the video for the Unit 8 review, and here's our first problem. Find the inclination of x minus 3y equals 9. So, the definition for an angle of inclination is simply the angle that this line forms with the x-axis, and that has to be a positive angle. So, your definition would be tangent of, and we typically use alpha for an angle of inclination, so tangent of alpha and tangent of that angle of inclination will always equal the slope of your line, m. Okay, so let's go ahead and graph this line to get a really good picture right here. And again, this angle of inclination has to be in the open interval from 0 to 180 degrees. It needs to be a positive angle. So, to get a graph of this, let's just go ahead and solve for the y. So I would subtract x from each side to get negative 3y equals negative x plus 9. And then let's divide everything by that negative 3 to get y equals negative x divided by negative 3 would be 1/3 x. And then 9 divided by negative 3 would be a minus 3. Okay, so it looks like our slope is 1/3. So let's use the definition. Oh, let's graph it first though. So I hope you guys see the y-intercept is negative 3. And then I have a slope of 1/3. So I'm going to rise 1 and run 3. And then I'm going to get out a ruler and I'm going to draw the perfect line. And do you see this angle right here that we like to call alpha? That is the inclination of this line. We call that alpha an angle of inclination. So, how are we going to find it? With this definition, tangent of our angle of inclination has to equal the slope of the line. So we're going to go tangent of alpha equals 1/3. And now, get out your calculator and make sure you're in degree mode. And let's go inverse tangent of 1/3. So alpha is approximately, so I'm going to get out my calculator, turn it on, and I'm checking my mode. I'm in radians right now, so I'm going to go to degrees. Okay, I highlighted degree. And now let's go ahead and punch out the inverse tangent of 1/3. So second tangent for inverse tangent of 1 divided by 3. And I'm getting approximately, and this is to the nearest degree, so that'd be approximately 18 degrees. So guess what? That angle alpha right there, 18 degrees. There you go. That's all there is to this. Okay? Now, had my calculator given me a negative angle right there, like say it was negative 18 degrees, that means my line would have had a negative slope. So if that were the case, then I'd take the negative 18 degrees and add 180 to get the positive angle with the x-axis. And that would give me an angle between 0 and 180. All right, number 2. Solve 5 cosine of theta equals negative 1 to the nearest tenth of a degree. So the first thing I'm looking for on a test is, can you solve for your trig functions? Simple algebra. So let's take this and divide both sides by 5 to get cosine of theta equals negative 1/5, and then we got to solve for that theta, so let's go inverse cosine of both sides. So that implies theta would be inverse cosine of negative 1/5, and we're already in degree mode, so let's just go ahead and punch that out. So I'm going to go second cosine for my inverse cosine of negative 1 divided by 5, and I'm getting to the nearest tenth of a degree, 101.5 degrees. Okay, now you know that there are many angles theta for which this equation would be true. So let's draw our unit circle and let's approximate the terminal ray for 101.5 degrees. That'd be right there in quadrant 2 somewhere. 101.5 right there. And then you think to yourself, in what other quadrant is cosine negative? And since cosine measures horizontally, that would be quadrant 3. So let's take this terminal ray and reflect it in the x-axis to get that terminal ray right there. Now, what would be the easiest way to find that positive angle right there? How about we go, we're in degrees, so picture 360 minus 101.5. So let's punch that out. 360 minus 101.5, and I'm getting 258.5 degrees. So 258.5 degrees, and let's put our answer up here. Now, it looks like we're done, but look at something else. They did not give us an interval for our angles theta right here. So we need to assume that they want all possible solutions. So that's easy. Just take your quadrant 2 angle and your quadrant 3 angle, all right, and add to each of them any multiple of, since we're in degree mode, any multiple of 360. So I'm just going to go plus n times 360 degrees. And same thing here, plus n times 360 degrees. And n is any integer, therefore these two answers give me every possible angle theta for which 5 cosine of theta equals -1. So always check, did they give you an interval? If they did not, you've got to deal with all solutions just like this right here. Okay, number 3. Solve 3 minus cosecant of x equals 7 to the nearest hundredth of a radian. Well, I know that I'm in degrees, so right now I'm going to change my mode to radian mode. And then I'm ready to first, let's go ahead and solve for cosecant. So I would subtract 3 from both sides to get negative cosecant of x equals 7 minus 3 would be a 4. And then I don't want this to be negative, so I'm going to multiply that equation by -1 to get cosecant of x equals -4. Now, there is not a cosecant button on my calculator, so if there's not a cosecant button, there's not an inverse cosecant. So how am I going to solve for this x right here? You guys remember your reciprocal relationships? Isn't cosecant the reciprocal of sine? And isn't the reciprocal of -4 -1/4? So let's just take this statement and take the reciprocal of both sides. So again, the reciprocal of cosecant of x would be a sine of x, and the reciprocal of -4 would be -1/4. So if cosecant of x equals -4, that implies sine of x would have to equal -1/4. We just took the reciprocal of each side. And now I can solve for this x, because to undo the function sine, we're going to do inverse sine of both sides. So that's going to give us x equals approximately, and we're already in radian mode, so let's punch out inverse sine of -1/4. Second sine for the inverse sine of -1 divided by 4. And I am getting to the nearest hundredth of a radian, -0.25. All right? So I'm going to get my unit circle out, and where is -0.25 on this unit circle right here? Wouldn't that be an angle in quadrant 4? About right there. So that angle right there is a negative angle because it's going clockwise, and that is my approximation of -0.25 radians. All right, now to answer this question, I don't want my negative angles, I need positive angles. So to find this positive angle right there, wouldn't I just go, I'm in radians, so 2 pi minus that 0.25? And that's going to give me that right there. So let's go 2 pi minus 0.25. And I'm getting to the nearest hundredth of a radian, 6.03. So my first x is approximately 6.03. And I'm going to put this right here because that's a quadrant 4 angle. And you guys know sine is also negative in quadrant 3. So let's find the quadrant 3 angle. And what we're going to do is reflect this terminal ray in the y-axis to get that terminal ray right there. And you guys know that this acute angle right here would also have to be 0.25. Forget the negative right there, all right? Because I'm talking about what is this angle? And that would be pi plus 0.25 more. So on the calculator, let's just go pi plus 0.25. Second, pi plus 0.25. And I'm getting to the nearest hundredth of a radian, 3.39 radians. And there's my two answers. But again, I am not done because they did not give me the interval from 0 to 2 pi. I've got to talk about all possible solutions. So I'm going to take those two answers and I'm going to add, and because I'm in radians, like the last problem we were in degrees, I think, so we did plus n times 360 degrees. Well, one rotation in radians would be 2 pi. So that would be x is approximately 3.39 plus any multiple of 2 pi plus 2m pi. And let's do the same thing with our 6.03 plus any multiple of pi plus 2m pi. And that is all possible angles x for which the equation 3 minus cosecant of x equals 7. Nice. Okay, same thing right here, and they gave us an interval this time, and I know I'm in radians, which my calculator is already in. So the first thing I'm going to do is solve for the trig function. Okay, let's solve for sine of 3x. And that's one step. Let's divide both sides by 2. So 2 sine of 3x divided by 2 would be sine of 3x. And root 2 divided by 2 is root 2 over 2. Ooh, I like that output. All right. So now let's think about this a second. Sine of 3x is root 2 over 2. Okay. Well, that means 3x would equal, and why do I have so many answers right here? I mean, my interval is 0 to 2 pi right there, right? But look at my equation. It is in terms of 3x. All right. So I want to know all of my possible 3x's. So instead of one rotation from 0 to 2 pi, I'm going to do 3 rotations, which would be 0 to 6 pi. But we'll get there in a second. Let's do this right now. When does sine have an output of root 2 over 2? Well, I see the angle right there. I hope you do too. And on the unit circle, the y-coordinate of that terminal point is root 2 over 2. So that implies sine of this angle equals root 2 over 2, which means 3x equals, and that angle is what in radians? That's right, it is pi over 4. So 3x has to equal pi over 4. Now, in what other quadrant is sine positive? And that would be quadrant 2. So let's reflect this ray in the y-axis to get this ray. And that would be another multiple of pi over 4. So 1 pi over 4, 2 pi over 4. That would be 3 pi over 4. And now I still have room for a lot more answers, and that's because they told me 0 is less than or equal to x, and x has to be less than 2 pi. So I've got to write this double inequality in terms of 3x. So we're multiplying all 3 sides by 3. 0 times 3 is still 0, but 2 pi times 3 would be 6 pi. So I'm going to have quadrant 1, quadrant 2, and then do 1 rotation for each of those, and then 1 more rotation with each of those, and that's going to get me to 6 pi, or 3 complete revolutions, 1, 2, and 3, giving me 4 more answers. So that's easy. Let's just take this pi over 4 and add 2 pi to it. And common denominators, 2 pi would be what? 8 pi over 4. So isn't pi over 4 plus 8 pi over 4? 9 pi over 4. And then let's add 8 pi over 4 to 3 pi over 4 to get 11 pi over 4. And now let's add 8 pi over 4 to this 9 pi over 4 to get a 17 pi over 4. And let's add another rotation of 8 pi over 4 to 11 pi over 4 to get a 19 pi over 4. So there are all of my possible 3x's right there. I have 6 of them. But I don't want to solve this equation for 3x. We want to know the angle x. So that means to solve for x, we're going to divide each of these angles by 3. So that means x equals, well, pi over 4 divided by 3 would be pi over 12. 3 pi over 4 divided by 3 would be pi over 4. 9 pi over 4 divided by 3 would be 9 pi over 12, which I'm going to reduce to 3 pi over 4. 11 pi over 4 divided by 3 would be 11 pi over 12, does not reduce. 17 pi over 4 divided by 3 would be 17 pi over 12, also does not reduce. And then 19 pi divided by 4 divided by 3 would be 19 pi over 12, which also does not reduce. So those are my exact answers in the interval. And these are x's now, and all of these x's are in the half closed interval. 0 is less than or equal to x, and x is less than 2 pi. Oh, that's a beautiful problem. Okay, number 5. Graph y equals 3 sine of x over 2. Give its period and amplitude. So first off, I hope you guys all see the period right now, or the amplitude would be a 3. So sine. You know what? I'm going to graph this. So I'm going to begin with what I visualize as my typical y equals sine of x. And again, there's my coordinate plane. And I know sine begins at the origin. All right. And then it's going to go up, down, down, and back up. Okay. And we're going to call this x. And we're going to call that y. And there's my what I picture as my sine curve right there, y equals sine of x. But this y equals sine of x has been transformed because now my a is not a 1, it's a 3. And I'm using my rule for amplitude is the absolute value of a. Well, the absolute value of 3 is 3. And the period is always 2 pi divided by b. Now, they're trying to trick you right here. This is x over 2. That means we're dividing by 2 or multiplying by 1/2. So the b is 1/2. So if I take 2 pi and I divide by 1/2, that's going to give me a 4 pi. Oh, here's my amplitudes right here. So I'm going to go up to 3 and have a min of -3. And then let's get back to that 4 pi. That means this x value at the end over here is going to be a 4 pi, making this x value in the middle a 2 pi, making this pi and this 3 pi. So there you go. And that is the perfect graph of y equals 3 sine of x over 2. And again, the amplitude is 3 and the period is 4 pi. Beautiful. Now you could check this on your calculator too if you wanted. Okay, now this time we're going from an equation or from the graph to an equation. So it's the same thing. Do you know your amplitude? Do you know your period? Do you know your horizontal and vertical translations? So I'm going to pick some key points right here, all right? This point, I could sure use that. And that's the point, x equals 1, y equals 1, 2, 3. And how about this point right there? And that's going to be x equals 1, 2, 3, and y equals -1 right there. Now with just those 2 points, I can get the perfect equation of the sine wave right here. So, do you see that we can clearly see if this were a cosine curve, it would have been horizontally translated 1 unit to the right. So anytime I'm asked to do the graph of a sine wave, I tend to use cosine because I know that y minus my vertical translation k equals a, the absolute value of my amplitude. Okay, I should say amplitude right there's fine, times cosine of b times the quantity x minus h. All right. So let's find our parts right here. Now, again, and I use this all the time for these type of problems right here. All right, so amplitude is, well, we have a formula for the amplitude, and that's going to be the max minus the min divided by 2. And that equals, well, the max is 3, the min is -1. 3 minus -1 would be 4 divided by 2, and of course 4 divided by 2 is 2. So my amplitude is 2. That's my A. I could put that here right now. Look at that. There it is. All right. Now what's the period here? Well, what's going to be the easiest spot to see this period? How about I go max to max right there? And that is how far horizontally? 1, 2, 3. That's 4 units. So the period is 4. And you guys know we use that period to find our B. This implies 2 pi divided by the B has to equal 4. 2 pi over B equals 4. Now let's just solve this equation for B. So I'd multiply by B and divide by 4. So is that B equals 2 pi over 4, which I would write as B equals pi over 2. That's my B right there. Okay. Now, next, my horizontal and my vertical translation. Well, right now I know I have y equals 2 cosine of pi over 2x, and if I can throw a minus h and a minus k, I am done. All right, so what's my k here? Well, there's a formula for k just like amplitude, except instead of a minus, we have a plus. That's the axis of this graph right here. That is the horizontal line that goes right through the middle of the sine wave. And that's going to be max plus the min divided by 2. And in this case, that is, well, 3 plus -1 would be 2 divided by 2, and 2 divided by 2 is 1. So my k is 1. So this function has been translated 1 unit up. All right, so that means I'm going to go y minus 1 right here. Okay, the new axis right here is this y equals 1. Okay, now the h. Well, this is why I use cosine. I can clearly see that a cosine curve was translated horizontally 1 unit to the right there. So that means my h is 1, and that means 1 unit to the right. This x is going to be x minus that 1. And there is the perfect equation to that graph right there. Okay? Hey, I checked this on a calculator, and I even put that axis of y equals 1 into it. So let's look at it on the calculator. So I probably did the same window. Oh, I did. Look at that. And look at the graph on the calculator. Now, I'm not saying you need to check these on a calculator, but again, here it is by hand, and here it is on the calculator. I think we have a winner. All right. I'm going to do one more problem here and then close up so I can get my people that are in class out of here. And you guys, I appreciate you guys working so hard and let me get this one recording together. Hope things are going fine. So number 7, let's finish off with this one, and then I'll stop the recording and we'll get my class out, and then we'll go to the rest of this after school's out today. So number 7. At Ocean Tide Dock, the first high tide occurs at 2 a.m. with a depth of 5 meters. So I know I'm going to do a graph, and I'm going to start my horizontal axis at midnight, and I've got to plot the point 2, 5. So here's my pretty rough, and this sketch does not have to be perfect by any means whatsoever. All right, you know, I try to do a real good job for my presentation here on the video, but all I'm going to do now is take this point. So you guys, again, make sure you have your horizontal axis in terms of time, and it looks like I'm scaling my hash marks by 2 hours there, and then do your vertical axis d of t, that's the depth of the water in terms of time, or y equals that, and those are scaled by 1s. So again, 2 a.m., 5 meters, 1, 2, 3, 4, 5, and my first point will be approximately right there. Now, what's my next point? The first low tide occurs at 8:30 a.m., and that would be 8.5 hours with a depth of 2.2 meters. So 8.5, 2, 4, 6, 8. So 10 would be about there, 8.5 right about there, and 2.2 meters. That's going to be approximately right here. And these points don't have to be perfect. Just make sure you label them. And understand this. What? The tides are periodic. And it's a little over 12 hours to go from high tide to high tide. So I'm going to take both of these points and I'm going to translate them 12 plus hours to the right. Nothing perfect there, and that, by the way, is why I didn't label anything beyond there, okay? But now I've got a pretty darn good sketch of this curve. There it is. Look at that. That's a winner. All right, so let's look at part A here. Sketch and label a graph showing the depth of the water at the dock as a function of time t after midnight, and we have done that perfect. So I'm going to say I'm done with part A. Now, the easy part, let's write a paragraph. Oh, I didn't see that paragraph. Write a paragraph to describe how you would use the given information about the high and low tides to find a trigonometric equation of this function. Well, how about let's just find the equation, okay? And if you want to write a paragraph about it, you may do so. But, if we show our work and we find this equation, I think that's better than any paragraph. All right, so what do we need? Amplitude, we need period, we need period to find our B, and then we need our horizontal and vertical translation. So, and you guys know, I can clearly see, if I use cosine, I have a horizontal translation of 2 units. So I'm going to use my y minus k equals a cosine of b times the quantity x minus h. And here's the same little chart I had earlier on the previous. So what is amplitude? It is max minus min divided by 2. So what's the max right here? Let's see if I skip the step. I think it's a 5. Nope, I'm doing general right now. So I'm going to go max minus min divided by 2. And that equals, all right, well, max 5 minus min 2.2. What would that be? 2.8? Divided by 2, and that's going to be 1.4. So the amplitude A is 1.4. Let's put that right there. Okay, now what's the period? Now, I'm like to think about the distance between these high tides right here, and I know it would be double the distance from high tide to low tide, and I'm talking about my input T right there. So can I go 8.5 minus 2, and that'd be 6.5, and then multiply it by 2 to get the whole way, and that would be 13 units right there. So this sine wave has a period of 13, which kind of surprises me with tides, because I've always been taught it's a little over 12 hours, but I guess it would depend on, where you're at in this world. Maybe they change if you're closer or farther away from the equator. Must be, huh? All right. So, we're at Ocean Tide Dock. That's got to be where? Well, that looks almost like northwest somewhere to me. Okay, anyway, let's keep going here. Now, let's use this period to find our B. And I could ask Cameron right now, and he'd tell me 2 pi over b has to be 13. Thank you, Cameron. You just helped on the video. All right, so let's solve for b. So multiply by b and divide by 13. So b is going to equal 2 pi over 13. All right, now you guys, you can leave this exact, and if you're more into approximating this with a decimal, you may do so, but I like exact answers. So I'm going to do my general sine wave right now in terms of cosine without the translations. All right, let's put the 2 pi over 13 in there, right there, and now I have y equals 1.4 cosine of 2 pi over 13 times x. Now I just need a horizontal and a vertical translation. Okay, so the K. Well, the K is what? It's the axis. And the formula for the axis would be the max plus the min divided by 2. So max 5 plus min 2.2, that'd be 7.2 divided by 2, 7.2 divided by 2, and that's going to give me a 3.6. So the horizontal line that goes right through the middle of this sine wave would be y equals 3.6. There it is. Look at that. Beautiful. All right. So that means this sine wave has been translated 3.6 units up. So I'm going to take this y and go y minus 3.6. And now I am almost done. All right. What's the horizontal translation? Well, this is why we use cosine right there. And this cosine function has been translated 2 units to the right. So the right would be a minus 2 units, minus 2, so this x becomes x minus 2. All right, h is 2, x minus 2. So y minus 3.6 equals 1.4 cosine of 2 pi over 13 times the quantity x minus 2 is the perfect equation for this rough sketch right here. And now we can use that to answer questions. So, I don't know. I think this little box right here is better than any paragraph I could write. So I'm going to say check. Okay. So in the next section on the review, we're going to be simplifying trigonometric expressions. All right, and this leads to trigonometric proofs, which we'll be doing a lot more of in Chapter 9. So to simplify a trigonometric expression, basically, you just use your known trig identities to try to rewrite and simplify. So if I look at something like 8a here, cotangent of a times the quantities secant of a minus cosine of a, well, I've got 3 different trig functions in this expression. So many times when you have multiple trig functions, if you use like your reciprocal relationships to convert everything into terms of sine and cosine, things will start canceling out and cleaning up rather quickly. So that's probably what I'm going to do with something like this. And here's the reciprocal relationships right here. So I'm going to use the one for cotangent and secant. And I see cotangent of theta is cosine of theta over sine of theta. Secant of theta is 1 over cosine of theta. So see this cotangent of A? I'm going to write that as cosine of A over sine of A. The secant of A, I'm going to write as 1 over cosine of A. And then this minus cosine of A, I'm going to leave alone. We love cosine of A. All right. Now, if we distribute this cosine of A over sine of A to both terms in the parentheses, we're going to see some canceling. So let's see what happens here. Well, if I distribute the cosine of A over sine of A to the 1 over cosine of A, the factors of cosine will cancel, leaving me 1 over sine of A. Looks simpler already. And then cosine of A over sine of A times negative cosine of A would be minus cosine squared of A over sine of A. Now, you look at this expression. Well, it's in terms of sine and cosine, so we can probably do a lot with this. And the first thing I would notice is I have a common denominator. So let's write this as 1 fraction with a common denominator of sine of A. And that would give me a numerator of 1 minus cos squared of A. Now, 1 minus cos squared of A is one of our most famous identities because you get this from the Pythagorean relationships right there. And look at this very first one, sine squared of theta plus cos squared of theta equals 1. Well, if we took this identity right here and subtracted cos squared from both sides, we'd have sine squared of theta equals 1 minus cos squared of theta. So this 1 minus cos squared of A, we can write as sine squared of A. So what I did, I skipped a step, I'm sorry, but sine squared of A over sine of A, well, a factor of sine cancels out, leaving just sine of A. And I'd say that is much simpler than our original cotangent of A times the quantity secant of A minus cosine of A. QED. Okay, so let's go to 8b. Ooh, okay. I see my cofunction relationships right here with these complementary angles. So look at that sine of 90 minus theta. Well, isn't sine of 90 minus theta? Cofunction relationships, sine of 90 minus theta is cosine of theta. All right, and that is because sine and cosine are nothing more than horizontal translations of 90 degrees of each other. So we can rewrite this sine of 90 minus theta as that cosine of theta. So we're going to get cotangent of theta over cosine of theta. And now the same thing, let's use reciprocal relationships to rewrite cotangent in terms of sine and cosine. And instead of dividing by cosine, I'm going to multiply by the reciprocal of cosine. And let me show you that in a second. But first, let's talk about cotangent of theta with our reciprocal relationships. And of course, cotangent of theta is cosine of theta over sine of theta. So there we have it. And we're dividing by cosine of theta, which is the same thing as multiplying by 1 over cosine of theta. And now do you see that the cosine of thetas cancel? And that's going to leave me 1 over sine of theta. And I'm going to use my reciprocal relationships again because look at this. Cosecant of theta equals 1 over sine of theta. So that's going to simplify to cosecant of theta. And there you have it, 8b. Okay, let's try 8c. Oh, secant plus tangent minus sine. Okay, so we're likely going to use our reciprocal relationships, and we're going to write everything in terms of sine and cosine here again. All right, yeah, the reciprocal relationships, and I've got secant and tangent, so I'm going to use this one and this one right there. So the secant becomes 1 over cosine of x, plus the tangent becomes, and the tangent, let's write that, instead of 1 over cotangent, let's write that as sine of x over cosine of x, because doesn't that give me a common denominator? All right, and speaking of that, let's use the common denominator. So the common denominator in this first grouping would be cosine of x, and my numerator becomes 1 plus sine of x. Oh, now I am very excited because do you guys see the 1 plus sine of x times 1 minus sine of x? Isn't that difference of squares? A plus b times a minus b equals a squared minus b squared. So a would be 1. 1 squared is 1. So I see 1 plus sine of x as 1 minus sine of x as 1 minus sine squared of x. Okay? And again, this is one of our most important identities right here because this we get from the Pythagorean relationships. Right here. So you see the first one, sine squared of theta plus cos squared of theta equals 1. Well, if I subtract sine squared from both sides, I get cos squared of theta equals 1 minus sine squared of theta. So this numerator becomes cos squared of theta, and then I have common factors that cancel. So that's going to equal, well, cos squared over cosine would just be cosine of x. And another problem done. I love simplifying trigonometric expressions. It is great to be able to take something looking so complicated and make it look so simple. This is really important stuff. All right, 8D. Oh man, we have cotangent, we have cotangent, and we have cosecant squared. Again, we're probably going to go some reciprocal relationships here. So, first off, let's take this cotangent right here and write it as cosine of A over sine of A. And let's take the tangent and write that as sine of A over cosine of A. Now, I don't have a common denominator, but I will in a moment. And let's take this cosecant squared of alpha. Now, isn't that 1 over sine squared of alpha? So instead of dividing by 1 over sine squared of alpha, we can just multiply by sine squared of alpha, just like that. Okay, now I'm not going to do anything else until I write this grouping with a common denominator, one fraction. Then I can cancel. So my common denominator, though, is this time sine of alpha times cosine of alpha, which means this cosine would have to be multiplied by, because it's only over sine right now, so I've got to multiply the cosine by cosine to get a cosquared of alpha. And I'm going to have to multiply this sine by sine of alpha to get plus sine squared of alpha. Now, do you see what I see? Pythagorean relationships. Again, this is our most important identity right there. All right, sine squared of theta plus cos squared of theta equals 1. So, commutative property of addition, sine squared of theta plus cos squared of theta, that numerator becomes a 1. And I have factors of sine of alpha. Was I saying theta earlier? That's an alpha. I have factors of sine of alpha that are going to cancel. So I'm going to be left with a cosine of alpha in my divisor here and a factor of sine of alpha outside right there. And I see a sine of alpha over cosine of alpha. Ooh, isn't that one of my Pythagorean relationships? You see sine of theta over cosine of theta? That is nothing more than tangent of, in this case, tangent of alpha. There you go. There's 8a through d, and we simplified all of them. That's great. All right. Now, for 9a and 9b, we're going to solve. Okay, so we're going to solve for x in each of these. Okay, so the very first one. Well, when does 2 cosine of x equal sine of x? Now, I would love to be able to divide by cosine and not have to worry about losing a root if I did so. And think about that a second. If I'm dividing both sides by cosine, that means cosine cannot equal 0. When cosine equals 0, is that a possible solution to this equation? No, it is not. So I can go ahead and do that. So if I divide the left-hand side by cosine, I'm going to get a 2. And the right-hand side, sine divided by cosine, well, sine over cosine is tangent. So 2 equals tangent of x. Okay, and we could do that again because cosine of x, or when cosine of x equals 0, that cannot be a solution to this equation. So cosine of x equals 0 is not a solution. So now I just have to solve 2 equals tangent of x, which means I'm going to inverse tangent both sides. So x is approximately inverse tangent of 2. The angle whose tangent is 2. And I did not tell you whether I wanted that angle in radians or degrees, so let's think about this. The angle whose tangent is 2. Well, let's go radians here. So go to your calculator and mode. I'm in radians already. Are you? So let's go second quit and punch out inverse tangent of 2. Second tangent for the inverse tangent of 2, and that equals in radians. And I also did not tell you what to round to, so I'm getting this 1.107148718. And if I did not tell you what to round to, as long as you round your answer appropriately, all right, I have to give you full credit. I'm betting I called that a 1.11. Yes, I did. Okay, and notice the comma there, because is there another angle in which tangent of x equals 2? Well, yeah, there's infinitely many. So let's draw our unit circle. And 1.11, well, pi over 2 would be 1.57. So 1.11 would be here in quadrant 1. And that is not exact by any means. It's ballpark. All right. And then I think to myself, in what other quadrant is tangent positive? Well, remember, tangent is sine over cosine. So sine and cosine would have to have the same sign. All right, and in quadrant 1, sine of x and cosine of x would both be positive. That's why we have that. And in quadrant 3, they are both negative. So I'm going to take this terminal ray right here, and I'm going to rotate it pi radians about the origin. Just like that right there. And now what is this angle? Well, wouldn't that just be 1.11 plus pi? A half a rotation. So pi plus 1.11, let's go. Second pi plus 1.11 into the nearest hundredth here, I'm getting 4.25. So there's my second x. Now, am I done yet? Well, in this equation, did they give me an interval for my possible angles? I did not. All right, so I did not give you an interval, so you have to talk about all possible angles x in which 2 cosine of x equals sine of x, or when tangent of x equals 2. So just take those two angles in radians, and since we are in radians, aren't we going to add any multiple of 2 pi to those? So I'd go plus 2m pi, plus 2m pi.
Set.
And there's all solutions right there. I'm sorry for the interruption on the announcement. All right. Now let's go to 9b. Sine of x equals cosecant of x. Well, oh man, when do those two functions equal each other? Oh man, if you could visualize those graphs right now, you could answer this question. And I believe, let's see, picture sine. I think it's like pi over 2 and then 3 pi over 2, but that's just me visualizing. Let's solve. And if I'm going to solve this, I better take this cosecant of x and write it in terms of sine, so I have everything here in terms of sine. And for that, I'm just going to use my reciprocal relationships, and cosecant of x equals 1 over sine of x. So if that's the case, sine of x cannot equal 0. All right, cool. So 1 over sine of x, could I multiply both sides by sine to get sine squared of x equals 1 over sine of x times sine of x? That's just a 1. Oh, I like that. So if sine squared of x equals 1, that means sine of x would equal plus or minus the square root of 1, or just plus or minus 1. There it is, plus or minus 1 right there. So when does sine have an output of plus or minus 1? And notice the unit circle over here. Sine measures vertically, so that'd be at pi over 2. Okay. And then at, how about this ray down here, which that'd be pi over 2, 2 pi over 2, that's 3 pi over 2. Okay, there you have it. Now again, I did not give you an interval, so we've got to talk about all solutions. So let's take those two particular solutions that are within 1 rotation of the unit circle, and let's add to each of those. We're in radians, so let's add any multiple of 2 pi, which would be plus 2m pi on both of them. And there you go. So 9A, 9B in the books. QED. So let's go to number 10. 10 part A. Oh, this one looks kind of complicated here. 2 cos squared of theta plus 3 sine of theta minus 3 equals 0. Well, that's a trigonometric equation, and it's almost in quadratic form there, isn't it? The only thing is, I have 2 trig functions. I have cosine squared, and I have sine. So wouldn't it be great if I could rewrite everything in terms of sine? Pythagorean relationships, you guys. See that cos squared of theta? Well, Sine squared of theta plus cos squared of theta equals 1, and that tells me that cos squared of theta would have to equal 1 minus sine squared of theta. Oh yeah, there it is. Now let's distribute the 2 to both terms. So I've got 2, and then I've got a negative 2 sine squared theta, and then I've got the plus 3 sine theta minus 3 equals 0. Now let's put this trig equation in quadratic form, and that means we need everything on one side with our sine squared term being positive. So I'm going to move this 0 over here to the left, which means I'm adding 2 sine squared theta to both sides, and I'm subtracting that 3 sine theta minus 3 sine theta, and if I combine my 2 and my minus 3 to get negative 1, I'd have to add 1 to get a plus 1 over there on the right. Now my trigonometric equation is in terms of one trig function, sine of theta, and we have it in quadratic form. So now we just factor. So let's see, 2 sine squared of theta, would that be 2 sine of theta times sine of theta? And then I need two numbers whose product is positive 1, but when I FOIL this thing out, I'd need to get a negative 3 sine of theta. So that tells me I'm going to have to use a minus 1 and a minus 1. Now, by the zero product property of algebra, one of these two factors has to equal 0. So that tells me sine of theta could equal 1/2, or sine of theta could equal positive 1.
Testing 1, 2, 3. Check.
Okay, sorry for the interruption again. This is what happens when I record at school. All right, anyway, well, I think we know when sine of theta has outputs of 1/2 and 1. And to answer that, I'm going to break out my unit circle right here. And doesn't sine have an output of 1/2 at, and in what mode am I in? Oh, little note down there, we're going to do this in degrees. Well, so wouldn't that be 30 degrees? About right there. Okay. And then, wouldn't it also be 1/2 over here in quadrant 2?
So, is that pretty loud?
And to get that, let's reflect the 30 in the y-axis to get that terminal ray right there. And that would be what? Well, that's going to be 180 degrees minus 30 degrees, so that's 150 degrees. Okay? And then how about the 1? Well, that would be at 90 degrees right there. And there it is right there. So we have theta equals 30 degrees, 90 degrees, and 150 degrees. And there's no interval, so you guys know we have to do what? We have to add any multiple of 360 degrees to those three answers to get theta can equal 30 degrees plus n times 360, 90 degrees plus n times 360, and 150 degrees plus n times 360 degrees. And there are all possible solutions of theta right there. All right, 10b, and I think 10b is it. Wow, but this one's awesome. Let's think about this. We have a cosine of theta times cotangent of theta equals 2 cosine of theta. So, well, notice that we have a factor of cosine on the left and on the right. So how about we subtract the 2 cos theta from both sides, or you could go the other way, it doesn't matter, and then we can factor. All right, so I'm going to bring everything over here to the left. So I'm going to have a cosine of theta times cotangent of theta minus 2 cosine of theta. And now each term has a factor of cosine of theta, so let's factor that out. And the distributed property, this would be cosine of theta times cotangent of theta, and cosine of theta times negative 2, minus 2 right there. And now by the zero product property of algebra, one of these two factors will have to equal 0. So that implies cosine of theta equals 0, or cotangent of theta equals 2. Let's find those right there. Well, we can do the cosine of theta equals 0 without a calculator. So, and I'm taking this one, and cotangent of theta equals 2. So I'm going to do the reciprocal of each side so I can use my calculator. So if cotangent of theta equals 2, that implies tangent of theta would equal 1/2. Note just the reciprocal of each side. Now we're ready to find our thetas. Let's break out the unit circle. So when does cosine have an output of 0 in degrees? And that would be at 90 degrees, right there, and at 270 degrees, down there, and that's it for one rotation. So when does tangent of theta equal 1/2? So we're going to have to do inverse tangent of both sides right here. Let's get that 270 in there. So get out your calculator. Let's double check and make sure we are in degree mode still. I think we are. Let's see, mode. Nope, I'm in radians, so that's why I always check. Degrees. Second quit. All right, so I need to solve for this theta right here, I'm going to need inverse tangent of both sides. So theta equals inverse tangent of 1/2. Second tangent for my inverse tangent of 1 divided by 2. And that's going to be, did it say what to round to here? Did not. So I probably did something like 26.57, maybe 26.5 degrees. Let's find out, or 26.6. So I'm going to go 26.6 degrees right there. And let's go ahead and graph that on our unit circle to 26.6 degrees. Something like that. And now think carefully, in what other quadrant is tangent positive? And again, tangent is sine over cosine, right? So what do you got to do here? All right, let's rotate 180 degrees about the origin, and then this angle would be 180 plus 26.6 degrees more, and that'd be what, 206.6 degrees? And there you go. And
Testing 1, 2, 3. Check, check.
oh, I'm going to make a phone call and somebody's going to get it. Okay, anyway, I'm sorry. I'm going to try not to be frustrated. They're obviously working on the intercom system for some reason during our office hours. All right, I guess it's better than during class time. So here we have it. Those are my 4 solutions within one rotation. But one more time, I did not give you the interval from 0 to 360 degrees. So I've got to talk about every possible solution. So you got your 90, your 270, your 26.6, and your 206.6. And to each of those, we're going to add any multiple of 360. So theta equals 26.6 degrees plus n times 360 degrees, 90 plus n times 360 degrees, 206.6 degrees plus n times 360 degrees, and then finally 270 degrees plus n times 360 degrees. And that is every possible angle theta. That is the solution to our original equation, cosine of theta times cotangent of theta equals 2 cosine of theta.